Hello everyone, my name is Seyyed Sarfjoo. I'm from Idiap Research Institute, and I'm here to talk about the speech activity detection based on multilingual speech recognition system. This is the common work between me and my colleague Srikanth Madikeri and Petr Motlicek. First, actually, briefly we introduce the speech activity detection, and after that talking about the multilingual acoustic modeling and the methods actually for training this multilingual acoustic modeling in the automatic speech recognition. And after that, as a proposed methods, we talk how to actually use this multilingual ASR-based model for the speech activity detection, and after that, talking about the experiments and results what we get. We can define the speech activity detection as a process for identifying the speech segments in an audio utterance. And we know actually nowadays is a critical part for majority of the speech-based application, including the automatic speech recognition, speaker recognition, speaker diarization, and many other fields. And developing domain invariance and the noise-robust speech activity detection is still actually is an active research field. There are many ways actually to categorize the works in the past 2 decades, but we can categorize this as optimizing the features for this speech activity detection, or optimizing the classifiers. For instance, using the support vector machine is investigated here, Gaussian mixture model, and the Ang works in 2012. Hidden Markov model in the basis work actually was investigated, and with the advent of the deep neural network, many papers actually applied the DNN-based model for speech activity detection. And convolutional neural network, recurrent neural network for modeling the sequence, and recently actually attention-based Saeed actually is in the leads, and some other words. Other field relevant to actually this work actually is training this multilingual acoustic modeling for automatic speech recognition, which is investigated in many works. And what we did here as a proposed method is applying this multilingual acoustic modeling as speech activity detector. Multilingual acoustic modeling is the effective way for compensation of the data shortage in low resource languages. Usually we have 2 methods for creating this acoustic modeling for ASR in a multilingual approach. The first, which is called the single task, is the concatenation of this PDF or probability density function from all the languages, and train this in which is in the last layer actually on the DNN architecture which we have. But on the other hand, multitask actually approach consider each of these languages as a separate layer in the output layer, and this approach actually is shown to be much more scalable with respect to actually single task approach. And the loss which is used actually here is the Lattice-Free Maximum Mutual Information loss, as is shown here in the first equation. But the difference actually, this LF-MMI loss usually actually is common in the monolingual, in the training of the ASR models. But the difference actually here is language dependent. And all utterances actually belong to some specific target language. And the numerator graph and the denominator graph are the same, actually language dependent. And the final loss is the average or weighted sum of all these language-dependent losses. The main motivation actually for applying this multilingual ASR base for training this speech activity detection actually is on the robustness and the language invariability. When we use actually several languages for training, the expectation is this SAD model be language invariable. In addition, when we use different data sets, so when the type of the noise in each data set be different, so we expect it to be noise robust too. So as a result, we expect it to have the generalization ability actually in the final model that we have. And for better modeling the contextual information, we consider the index of the maximum output posterior as a binary decision function. This actually comes from this prior knowledge, which non-speech fonts are mapped to non-speech PDFs, and the speech fonts are mapped to the speech PDF. Then this comes mostly from the HMM-GMM models. So based on this, we can use the index of the maximum output posterior as a binary decision function. For instance, here, if in this plot, in this figure, sorry, if this maximum output posterior actually be between the first and the fifth one, so we consider this as a non-speech. And if this is more than this, we consider this as a speech. So in the multilingual ASR architecture, so we have per language, we have some output posteriors. So based on this function, we can get speech, non-speech actually label per frame for each of these languages. So on top of this, for combination, we use the logistic regression or majority voting for getting the final scores. So let's talk about the datasets which we use. For training, we use the BABEL 18 languages from the BABEL datasets, which are approximately 1,000 hours of the data. And in the table 1, you can see the list of the dataset which is used. And here we must mention actually all the data are from BABEL except Somali, which is from material projects. For showing this language invariability and the domain robustness of this model, we start evaluating our model in 3 different data sets. BABEL Kurdish is the conversational speech actually in the Kurdish language. LiveATC is the conversation between the controller and pilots in English language, but this is challenging because the accent variability and the noise type actually for the pilots is so variable. And Easter 2 is broadcast news dataset in the French language. In table 2, you can see the duration and the number of segments for each of these datasets. And for each of them, we consider dev and evaluation. And we consider 2 types of the experiments, in-domain and out-of-domain. And in-domain is the condition we have access to the dev sets, we consider it. And for out-of-domain is the condition we don't have access to this. As a pre-processing, we downsample all this speech actually to 8 kilohertz, and MFCC features we use as which is common in the ASR training, 40-dimension MFCC and 100-dimension online I vector as an input one. And we consider frame subsampling factor of the 3 for faster convergence, and for data augmentation, we use 2-fold speech perturbation. The network architecture contains each layer of the TDNN with 1024 nodes and 1 pre-final layer with only 200 units. As a post-processing, we consider temporal smoothing for better detection of the start and end of each segment. It means if the detected segment, for instance, is less than 300 milliseconds, we don't consider this as a segment. Detection error rates was considered as a performance measure when false alarm and mix detection is combined over the total duration of the speech in the reference file. For in-domain evaluation, between these 18 languages, the TalkBisin actually shows the best results, and we denoted this as a single best. But with this multilingual architecture, so we get improvements on top of this. With respect to this logistic regression, we get better results with respect to majority voting. As a baseline, we compare our model with Pyannote, which is LSTM-based architecture, and we train this with using the same datasets, 18. And we get comparable results, but Pyannote here shows slightly better, and using different architecture, we hypothesize is the main reason for observing these results. On the other hand, in out-of-domain scenarios, we got significantly better results with respect to the baseline. Here, we compare our model with, in addition of Pyannote, we compare with two pre-trained models. One of them is WebRTC, which is used in the DHART2 challenge. One of them is a phone recognizer, which is trained using Hungarian and DB. And we can see actually significant, we compare here the best, our model for this experiment, we consider single best. But if, for instance, if we have access to some development sense for the logistic regression condition, we can see even more improvement on top of it. And the same pattern actually we see in other data sets for the ISTER2. And we can see actually again, we significantly actually in this set based on DetER, we get improvements with respect to the baseline. And if we use this logistic regression on top of what we have, so we can even improve this further. It shows actually we can get generalizability, but still actually if we have in-domain data, we can even improve this more. So as a conclusion, this multilingual acoustic model is an effective way for training a noise-robust speech activity detection, and it helps to improve the generalization ability of these Seyyed models. And the proposed method that we showed actually was evaluated in domain and out-of-domain scenarios. Thank you very much for your attention.
Thank you to the speaker. Any questions from the audience?
Either online or in-house. If you're online and would like to ask a question, just put it in the chat.
All right, I have actually several questions, so okay. I will ask some. So first, I wanted to ask, how did you specifically choose these 18 languages, or do you think, did you try removing some of the portions of the vectors produced by basically the binary phone posteriors, and see how they would impact the voice activity performance, detection performance? For choosing this 18 language, actually, it was based on the availability, because we had access to this BABEL dataset, so we started using this one. And for DetER, we didn't compare it with all other datasets or other baseline models, but some internal evaluation actually, we see actually some. I didn't actually import this here, but for this misdetection, for instance, we get better results, but for the false alarm case, actually, it was a little deviated. All right, thank you. My other question is, since we are using ASR here, or acoustic model at least, basically we are modeling also the phone sequences. Do you think we could expect that when you have the inset languages, so that means one of the languages that it was trained on, the acoustic model, and you're running the SAD on that, if there is some speech disturbance, like let's say some restarts, you know, and things like that, do you think it would a little bit hurt the performance of the SAD based on the acoustic model that models the phone sequences? So if the phone sequence is not expected as expected, would it a little bit hurt the performance?
Oh, okay, but one thing actually about this phone sequences, this is, in my view, actually, it can be the strength of multilingual ASR conditions, because maybe some of the languages actually, because we have the separate categories for languages, and some of them actually can be robust to this, and some of them actually can show the weakness. So this is the power actually, we can actually somehow use this for alleviating this problem.
Thank you. And the last one is just kind of technical thing, and that is like on slide 12 or 13, I believe, when you're showing the false alarms and the miss rate. Well, kind of, I had two comments there, and one was that you're using the most aggressive setting for the WebRTC SAD. You set it to 3.
3, yes.
So that means it's basically throwing maybe more speech than it would be with the less aggressive setting.
No,
but still you have very high. You have higher false alarms than the miss rate, which is kind of surprising since you have the most aggressive setting.
Yes.
I would expect it to be the other way around, kind of.
Based on DetER detection error rates, actually we tune this on the depth set, and this 3 actually shows the best results. So we just use this, but
yeah, just that I would expect that the false alarms and the miss rate, the proportion would be the opposite way because of the aggressive setting. In basically.
Yeah, we set this, but. No, for other sets, we checked this. Yeah, it was reverse, but based on detection error rates, actually, because it was more. So this one actually shows the less detection error rates.
And the very last one, then I will stop. I promise. That maybe wouldn't be helpful to try to basically use a threshold and try to balance the false alarms and the miss rates, or basically to present EERs, equal error rates, rather than. Because we can choose any operating point between.
Yes, exactly.
Right?
Actually, based
so
on this.
Wouldn't it be better to balance it, to present ERs, to have basically the same FA and miss rate?
Yeah, that's true. Actually, this is for this case. Actually, currently, for instance, based on some depth sets, we can actually tune this, but for generalization, actually, in some total and synth set, maybe yes. Actually
for the SAD, because you could plot the whole death curves for the different systems that you have and compare them, not just for one, operating point, but
yes,
for
exactly.
any.
That's the
right. Thank you.
Thanks a lot.
Could, if you're looking at the ESTER data, could you remind us what were the languages for the ESTER data again?
For the ESTER?
I thought so. These were the 18 for BABEL. For the open set. The ESTER 2 corpus.
French. And none of these languages actually are common, if you mean actually.
With ESTER 2?
ESTER, yeah. We just used actually subset, which is French.
Okay, all right. Sorry, I was just trying to see whether things were completely separate.
Yes, exactly, actually. Okay. For instance, LiveATC, none of these languages are English. LiveATC is in English. None of them actually are in French, but the language actually are independent from each other.
So it's one of the advantages of looking at more traditional, I wouldn't say signal processing strategies, but you could have methods that are unsupervised, and those typically would be language independent. But when we move to network-based solutions, obviously they tend to be more tailored to the language that it's trained on. So this is a nice test.
Mm-hmm. Okay.
Any final questions from the audience or online? Oh, yes, we have one hand up in the back.
Thank you for the talk. For my understanding, VAD is almost don't stand alone, but it's for speech recognition, speaker recognition, and to evaluate the results of VAD without context, it's a little bit lack of some information. Did you try to use your VAD or some application like speech recognition or speaker recognition or other application to see how it improves the results of the end goal?
Well, that's a good question. Actually, for speech recognition, we didn't include this because we must first do some comparison with all methods, but we get near 1% improvement when from 7 to 8. But this evaluation wasn't completed because we must investigate other baseline methods actually on this.
Okay, let's thank the speaker again.